This week we're going to take a look at shear stress. Shear stress is different from axial stress. Axial stress, we'd be applying the force along that direction. Shear stress, we are applying it orthogonally along the direction there. So this is going to happen quite a bit. Getting ahead of myself. This is going to happen quite a bit with fasteners. You'll see this a lot. Nails, screws, bolts, rivets. And so in this situation here, we've got this bolt, and it's between two plates. The plates are flexing, pull it in different directions. Let's take a look what happens. So if I draw a free body diagram of what's going on right here and separate it out, I've got my bolt head C, and then I have a force F, equal and opposite force. I have a force F that's pushing along that way. And so what do I have? Well, I have to have an internal force that balances it out because it has to be in static equilibrium. So I have a force internally of, we'll call that P, that is pushing against the way that we're pulling. So internally, everything balances out. So if we take a look at that, we can figure that out. So we, with our lowercase Greek letter tau, we'll continue our classical Greek education here at Mass Maritime. So that's a lowercase tau, is equal to that load over the area. And since the external force is F, we can also say F over A. And so that will give us the shear stress. Now this is for what we call a single shear application, when we only have one shear force in the item. Now what's going on in the lab is we have something more along lines of this, which is a double shear application. So we have the shear force being applied over two surfaces, not one. So this, once again, we've got a plate here, and then two internal plates that are pulling back and forth that are applying forces to the bolt. So if I go and I take a look at, we're going to free body diagram it right here, and we're just going to pull out that little chunk and take a look at it. So what I have externally is I'll have that force that's being applied to the middle. Now I will have an internal force that balances it out. And once again, we'll call that force P. But I have it now applied over two surfaces. Since it is applied over two surfaces, our math changes very slightly because it's still the average shear force is going to be that internal force over the area. But now what changes is the magnitude of that shear force. Because if I do the sum of the forces in the x direction have to equal 0, and I say to the right is positive, well, what we've got is F minus P equals 0. So that means F is equal to 2P. So to accommodate this in our formula, we have F over 2A. And so this is a double shear application because now we have the force being carried over twice the area. And so as we apply the loads to these samples that we're going to use and they snap, we just have to remember that it's going to be over twice the area.